25 seconds.
Status check.
Go Atlas.
Go Centaur.
Go Lucy.
Seven, 6, 5, 4, 3, 2, 1, 0. Liftoff. Atlas V takes flight, sending Lucy to uncover the fossils of our solar system.
Tower clear. RD-180 propellant utilization has gone to closed loop control. The vehicle has begun the pitch yaw roll maneuver. Now, 30 seconds into flight, vehicle is 0.6 miles in altitude, traveling at 939 miles per hour. RD-180 performance continues to look good at this time. Engine pump speeds and injector pressures are in family for this thrust level. Atlas vehicle attitude remains stable at this time. Attitude rates near zero in all axes. Now at T plus 70 seconds into flight, vehicle is 4 miles in altitude, 0.2 miles downrange distance, traveling at 1,200 miles per hour. Mach 1, Atlas is now supersonic. Vehicle is now passing through max Q, maximum dynamic pressure. The vehicle is now throttling down slightly. RD-180 engine parameters continue to look nominal after the prior adjustment to the thrust level. Approximately 2 minutes remain in the Atlas booster phase of flight. The Atlas V rocket weighs now just 1/2 of what it did at launch, burning propellant at a rate of 2,600 pounds per second. Vehicle is now executing closed-loop steering. Centaur reaction control system is now pressurizing the flight levels.
So a beautiful launch sequence there. We do have another minute and a half or so to go with the booster in operation, getting Lucy.
We're now just under 3 minutes into flight. Atlas is 33 miles in altitude, 59 miles downrange distance, traveling at 5,600 miles per hour.
So Lucy being lifted up out of the atmosphere by the booster, getting on its way into a park orbit before we get towards...
All first stage vehicle systems are operating as expected at this time.
Future portions of the launch activity, we have the Centaur multiple burns ahead and spacecraft separation.
Yeah, the big milestone we should see, Josh, coming up is booster engine cutoff, which would be the first stage cutoff and then stage separation.
The main engine is now throttling to maintain a constant 5G acceleration limit.
We're going to see a few things happen pretty rapidly. The booster will cut off just after 4 minutes, and then within the next 15 seconds after that, we should see the Atlas separate from the Centaur, and then the Centaur engine ignite for its first burn.
Centaur has begun the boost phase chill down sequence, and the RD-180 is now throttling to maintain a constant 4.6 G acceleration limit. Boost phase chill down sequence has completed, and we have BECO, booster engine cutoff, and a successful stage separation event.
So what you're seeing on screen is an animation that's being driven by actual telemetry.
Please start on the RL-10.
So we are watching these things in an animation happen here, but they're happening in real time as well.
And MES 1, we have ignition for the first burn.
All right, so there we go. We should see the fairing jettison here.
We have indication of good payload fairing jettison.
And there we go. All right, Nick, so that wraps up the first round of major milestones here. Still very much in the middle of dynamic flight.
The PU system on the RL-10 is now in an open-loop burn-off mode to burn off excess fuel in the early portion of this burn.
So walk us quickly through, Mick, what are we looking for in this burn and the next one?
So this burn is going to end with MECO getting Centaur and Lucy into its park orbit around Earth. And then we will then get into MESS 2, which will get us into that transfer orbit, getting Lucy on its way.
Awesome. So that's going to do it for now. Finishing up the initial launch activities, everything sounding like it's going perfectly. Daryl, back to you.
The Lucy spacecraft will be taking a journey where no other spacecraft has gone before: the Trojan asteroids. The Trojans are two groups of asteroids that lead and trail Jupiter in its orbit around the Sun, and they've been trapped in these stable locations for over 4 billion years. Lucy will have a suite of scientific instruments for collecting data as it flies by the asteroids. LaLaurie is a long-range reconnaissance imager. It's often referred to as Lucy's Eagle Eyes, since it has the highest spatial resolution of all of Lucy's cameras. This black and white camera is actually a type of telescope, the same kind as the Hubble Space Telescope. LaLaurie was built to produce clear images of the Trojan's craters, which will be a challenge since the Trojan asteroids are extremely dark. LaLaurie will be able to see 75-yard-wide craters from over 600 miles away. That's like standing at one end of a football field and being able to see a fly at the other end. The instrument's simple design does not use optical filters and includes no moving parts, reducing the risk of part failure during the mission. LaLaurie will also search the Trojans for evidence of any rings and new satellites. The instrument's ability to see faint targets from far away also makes it perfect for optical navigation. LaLaurie will help Lucy navigate to a point in space, and then a terminal tracking camera aboard the spacecraft, known as T2CAM, will help the instruments accurately point towards the targets. LATES is Lucy's thermal emission spectrometer, which detects far infrared radiation emitted by the asteroids due to how they are heated up by sunlight. LATES detects this radiation using a small telescope to focus the incoming energy onto a detector, similar to the way a remote thermometer works. So, LATES is not taking images, but rather temperature measurements at various points on the asteroid. This data will be combined so that scientists can get an understanding of its surface properties. LATES will examine the properties of the regolith on the surface by measuring thermal inertia, which is the measure of how slowly the asteroid heats up from sunlight and then releases that heat. By taking the temperature readings at different parts of the asteroid, the Lucy science team can measure the thermal inertia and figure out how much dust, sand, or rock is present on the asteroid's surface. That data will tell us a lot about how the asteroid was formed, providing insight into the history of our solar system. Lucy's LaRalph instrument will search the Trojans for organics, ices, and hydrated minerals, and will help determine the surface compositions of the asteroids. LaRalph is actually two instruments in one, and together they will measure and analyze the spectra of light absorbed and reflected by the asteroid. The first is a color visible imager, the Multispectral Visible Imaging Camera, or MVIC. It takes visible light color images of the Trojan asteroids. The second is an infrared imaging spectrometer, known as LISA, the Linear Etalon Imaging Spectral Array, which collects infrared spectra of the asteroids. Like LaLaurie, LaRalph does not have a focusing mechanism. Instead, it is designed to stay in focus despite the extreme temperature differences in space by being made almost entirely from a single block of aluminum. As you can see, the Lucy spacecraft has a large suite of tools to study the Trojan asteroids, which will help us better understand the formation of our solar system.